At the surface of our planet, everything feels familiar. Cities rise from the ground, oceans stretch to the horizon, mountains pierce the sky. Beneath our feet lies rock, soil, and the foundations of the world we inhabit. Yet this thin outer layer, what we call the crusties, only a fragile skin covering something far deeper, far hotter, and far more mysterious. Directly beneath us, the earth begins to change. Temperatures climb, pressure intensifies. Solid rock slowly transforms into flowing material, moving at a pace so slow it is almost impossible to imagine. Hundreds of kilometers down, the conditions become extreme. Thousands of kilometers deeper, the environment becomes hostile beyond any human technology ever built. And at the very center of it all, 6,371 kilometers beneath the surface, lies the most inaccessible place on the planet. No human has ever been there. No machine has ever come close. The deepest hole ever drilled by humans, the Kola superdeep borehole in northern Russia, reached just over 12 kilometers. That is less than 0.2% of the distance required to reach Earth's center. Everything beyond that point must be reconstructed through indirect evidence, seismic waves from earthquakes, high-pressure laboratory experiments, and decades of geological modeling. Yet these methods have revealed something extraordinary. At that depth lies the inner core of the Earth's solid sphere of metal, roughly the size of the Moon. Surrounded by an ocean of molten iron, temperatures rival the surface of the Sun. Pressures exceed 3.5 million times the pressure at sea level. The conditions are so extreme that even the behavior of matter itself begins to change. But the deeper scientists investigate, the stranger the story becomes. Recent studies suggest the inner core may be changing shape. It may be rotating differently from the rest of the planet. Some evidence even indicates that its structure is not uniform but layered, with a hidden inner region inside the inner core itself, which raises unsettling questions. What exactly exists at the center of our world? How did it form billions of years ago, and could changes occurring 6,371 kilometers beneath our feet influence the planet we live on today? To answer those questions, scientists have spent decades decoding signals traveling through the Earth, teeny vibrations from earthquakes that carry the only direct information we have about the deepest place on our planet. What those signals reveal is a story of immense pressure, violent formation, and a hidden engine that quietly shapes the behavior of the entire Earth. Human civilization has mapped the surface of the planet with remarkable precision. Satellites orbit overhead, measuring the contours of continents, tracing ocean currents, and observing weather patterns across the globe. Aircraft fly through the upper atmosphere. Submersibles descend into the deepest trenches of the ocean. Yet the most inaccessible place on Earth is not above us or beneath the sea. It lies directly beneath our feet. At first glance, reaching the interior of the Earth might seem like a straightforward engineering challenge. Drill deep enough, build stronger machines, and eventually the center of the planet should come within reach. But the reality is far more unforgiving. The deepest humans have ever drilled into the Earth is just 12,262 meters, barely over 12 kilometers. This record was achieved by the Kola superdeep borehole, a Soviet scientific drilling project that began in 1970 on the Kola Peninsula in northern Russia. The goal was ambitious but scientifically simple: penetrate as far as possible into Earth's crust to better understand the planet's geological structure. For 2 decades, engineers pushed drilling technology to its limits. Specialized drill bits were designed to withstand immense pressure. Equipment was reinforced to operate at depths where conditions were poorly understood. Slowly, meter by meter, the borehole descended deeper into the crust. But long before reaching the mantle, the project encountered a barrier no machine could overcome: temperature. At around 12 kilometers deep, temperatures inside the borehole reached 180 degrees Celsius, far hotter than scientists had predicted. Rock at that depth did not behave like the stable, solid material engineers expected. Instead, it began to deform and flow under pressure, closing in on the drilling equipment and making further progress nearly impossible. Drill bits warped, equipment failed. The rock itself began acting almost like plastic under extreme heat and pressure. Continuing deeper would require materials capable of surviving conditions far beyond the limits of conventional engineering. In 1992, the project was halted. The Kola Super Deep borehole remains the deepest direct exploration of Earth ever achieved. To put this in perspective, the center of the Earth lies 6,371 kilometers below the surface. The deepest hole humans have drilled covers less than 0.2% of that distance. Even if drilling technology advanced dramatically, the challenges only intensify with depth. Temperature rises rapidly as one moves downward through the planet. This increase is known as the geothermal gradient, and in the upper crust it averages roughly 25 to 30 degrees Celsius per kilometer. At depths of hundreds of kilometers, temperatures exceed 1,000 degrees Celsius by the time one approaches the continental boundary at 2,900 kilometers. Temperatures are estimated to reach 3,500 to 4,000 degrees Celsius. At the center of the Earth, temperatures are believed to reach 5,000 to 6,000 degrees Celsius, similar to the surface of the Sun. Pressure increases even more dramatically. At sea level, the pressure we experience is defined as 1 atmosphere. At the center of the Earth, pressures exceed 3.6 million atmospheres. Under such conditions, even the atomic structure of materials can behave differently. No drilling equipment, no spacecraft-grade alloys, and no currently known materials could survive those extremes long enough to penetrate thousands of kilometers into the planet. So if direct exploration is impossible, how do scientists know what exists beneath the surface? The answer lies in earthquakes. Every time an earthquake occurs, it releases energy that travels through the Earth in the form of seismic waves. These waves propagate outward from the rupture point, moving through the planet's interior before being detected by seismometers across the globe. Much like medical ultrasound or CT scans allow doctors to visualize the interior of the human body, seismic waves allow geophysicists to reconstruct the internal structure of the Earth. But seismic waves behave differently depending on the material they pass through. Some waves, called P waves or primary waves, can travel through both solids and liquids. Others, known as S waves or secondary waves, can only move through solid materials. When these waves encounter boundaries between different layers inside the Earth, they bend, reflect, or disappear entirely. By measuring how long it takes for these waves to reach distant sensors, and by observing how they change direction or vanish, scientists can infer the composition and physical properties of the planet's interior. In the early 20th century, this method began revealing something unexpected. Seismic waves were not traveling through a uniform planet. Instead, they were passing through a series of distinct layers, each with dramatically different physical properties. Some waves slowed down, others sped up, some vanished completely before reappearing thousands of kilometers away. These anomalies pointed to something extraordinary hidden deep inside the Earth. A massive liquid layer surrounding an even denser solid center. A structure no human could ever reach, but one that could be detected through the faint vibrations of distant earthquakes. The deeper scientists looked into the data, the clearer the picture became. Beneath the crust, beneath the mantle, and nearly 3,000 kilometers down, there exists an ocean of molten metal. And inside that ocean lies a solid sphere of iron under pressures so immense that it remains solid despite temperatures hot enough to melt steel. The center of the Earth had begun to reveal itself not through exploration, but through the language of seismic waves. To understand what lies 6,371 kilometers beneath the surface, scientists first have to travel back in time more than 4.5 billion years. To a period when Earth did not yet exist as a finished planet. At that time, the solar system was a violent and chaotic place. A vast cloud of gas and dust surrounded the young sun, slowly collapsing under gravity into a rotating disk. Within this swirling disk, microscopic grains of rock and metal began colliding and sticking together. Over time, these tiny particles grew into larger fragments, then into kilometer-sized bodies known as planetesimals. Collisions between these objects were constant and often catastrophic. Some impacts shattered bodies apart. Others fused them together, gradually building larger and larger worlds. This process, known as planetary accretion, continued for tens of millions of years, eventually forming the rocky planets of the inner solar system: Mercury, Venus, Mars, and Earth. But the early Earth was nothing like the stable world we recognize today. The energy released during continuous impacts generated immense heat. Every collision converted kinetic energy into thermal energy at the same time. Radioactive elements such as uranium, thorium, and potassium were decaying inside the young planet, adding even more heat to the interior. As a result, early Earth became partially or possibly almost entirely molten. Instead of solid rock, much of the planet existed as a vast ocean of liquid material. Geophysicists often refer to this stage as the magma ocean phase. Inside this molten world, gravity began to reorganize the planet's internal structure. Different materials have different densities. Metals such as iron and nickel are significantly heavier than silicate rocks, which dominate Earth's crust and mantle today. When the planet's interior melted, these density differences allowed materials to separate. This process is known as planetary differentiation. Heavier elements sank toward the center. Lighter materials floated upward. Over time, enormous quantities of molten iron and nickel migrated downward through the magma ocean, forming the earliest version of Earth's metallic core. Laboratory experiments and computer simulations suggest that this separation occurred relatively quickly on geological timescales, possibly within tens of millions of years after the planet formed. As the metal descended, it carried enormous amounts of heat with it. The sinking iron droplets coalesced into larger masses, eventually merging into a single central reservoir of molten metal. This created the outer core, a deep layer composed primarily of liquid iron alloy. But the story does not end there. At extreme depths, pressure increases dramatically. As iron accumulated at the very center of the planet, pressures became so immense that the metal began to crystallize, forming a solid sphere within the liquid metal surrounding it. This solid sphere is what scientists now call the inner core. Today, the inner core is estimated to have a radius of about 1,220 kilometers, roughly 3/4 the size of the Moon. It is composed mostly of iron with smaller amounts of nickel and trace lighter elements such as sulfur, oxygen, or silicon. The surrounding outer core extends from roughly 2,900 kilometers below the surface to about 5,150 kilometers deep. It remains entirely liquid due to the balance between temperature and pressure conditions at those depths. But the early formation of the core had consequences far beyond simply reorganizing Earth's interior. It also created one of the most important features that makes life possible on this planet. As the molten iron in the outer core began to circulate, it generated electrical currents. Moving conductive fluids inside a rotating planet can produce powerful magnetic fields through a process known as the dynamo. This process eventually gave rise to Earth's magnetic field. The magnetic field extends far into space, forming a protective bubble known as the magnetosphere. Without it, charged particles from the sun known as the solar wind would gradually strip away the atmosphere. Scientists believe this may have happened to Mars, which lost much of its magnetic field billions of years ago. As a result, the Martian atmosphere slowly eroded, leaving behind the cold, dry planet observed today. Earth's core, however, remained active. The constant movement of molten metal deep within the planet continues to sustain the magnetic field that shields the atmosphere and surface from intense solar radiation. Evidence for this ancient process is preserved in rocks. When molten rock cools, iron-rich minerals inside it align with the magnetic field present at that time. By studying these magnetic signatures in ancient volcanic rocks, geologists can trace the history of Earth's magnetic field stretching back billions of years. These records reveal that the geodynamo has been operating for most of Earth's history, but while the basic structure of the core is now well established, many questions remain. How exactly does heat flow between the core and the mantle? How fast is the inner core growing as iron slowly crystallizes from the liquid outer core? And could the deep interior still be changing in ways scientists are only beginning to understand? To answer those questions, researchers had to reconstruct something that cannot be observed directly, the internal architecture of an entire planet, and that required learning how to read the signals traveling through the Earth itself. For most of human history, the interior of the Earth was a mystery shaped by speculation. Ancient cultures imagined underground oceans, vast caverns, or mythical realms hidden beneath the surface. Without tools capable of probing deep underground, the true structure of the planet remained beyond reach. That began to change in the late 19th and early 20th centuries with the birth of modern seismology. Every earthquake releases energy that travels through the earth in waves. These vibrations move through rock, pass through deep geological boundaries, and eventually reach sensitive instruments known as seismometers, sometimes thousands of kilometers away from the source. At first, scientists simply recorded the arrival times of these waves, but over time, researchers noticed patterns that hinted at something far more complex beneath the surface. Seismic waves did not travel through the earth at constant speeds. Instead, their velocities changed dramatically at certain depths. Some waves suddenly slowed down, others accelerated. Some disappeared entirely, only to reappear further across the planet. These strange behaviors suggested that seismic waves were encountering boundaries between different materials inside the earth. By carefully analyzing thousands of earthquake records from around the world, geophysicists gradually reconstructed the internal structure of the planet. What they discovered was a layered world. The outermost layer is the crust, the thin shell on which all continents, oceans, and ecosystems exist. Compared to the size of the Earth, the crust is astonishingly thin. Beneath the oceans it can be as little as 5 to 10 kilometers thick. Beneath continents it can reach 30 to 70 kilometers. Despite being the layer humans inhabit, the crust represents less than 1% of Earth's total volume. Below the crust lies the mantle, which extends to a depth of roughly 2,900 kilometers. The mantle makes up the vast majority of Earth's mass and volume. Although the mantle is composed of solid rock, it does not behave like the rigid stone familiar at the surface. Over extremely long timescales, mantle rock can flow slowly, deforming under heat and pressure. This slow movement drives the process of mantle convection, which ultimately powers plate tectonics, the movement of continents, and the formation of mountains, earthquakes, and volcanoes. Temperatures in the mantle increase steadily with depth. Near the upper boundary, temperatures may be around 500 to 900 degrees Celsius. Near the base, they rise to over 4,000 degrees Celsius. But the mantle is not uniform. One important boundary lies roughly 410 kilometers below the surface. At this depth, increasing pressure forces minerals within mantle rocks to rearrange their atomic structures. The result is a sudden change in density and seismic wave behavior. Another major boundary occurs near 660 kilometers deep, marking the transition between the upper mantle and the lower mantle. Again, changes in pressure alter the mineral structure of rocks, creating a distinct seismic boundary. Below this transition zone, the lower mantle extends for more than 2,000 kilometers, reaching down to the edge of Earth's core. At a depth of approximately 2,900 kilometers, seismic waves encounter one of the most dramatic boundaries inside the planet. Here lies the core mantle boundary. When earthquake waves reach this region, something remarkable happens. S-waves vanish completely because S-waves can only travel through solid materials. Their disappearance indicates that the layer below this boundary must be liquid. Meanwhile, P-waves capable of traveling through both liquids and solids slow dramatically and change direction as they pass through the region. These observations led scientists to a profound conclusion. Beneath the mantle lies a massive ocean of molten metal. The outer core. The outer core extends from about 2,900 kilometers to roughly 5,150 kilometers beneath the surface. It is composed primarily of liquid iron mixed with nickel and lighter elements such as sulfur and oxygen. Temperatures within the outer core range from approximately 4,000 to over 5,000 degrees Celsius. The liquid nature of this layer is not only inferred from seismic evidence, it is also essential to explaining one of Earth's most important features, the magnetic field. But the structure of the core revealed an even deeper surprise. In 1936, Danish seismologist Inge Lehmann noticed subtle reflections of seismic waves that could not be explained by a completely liquid core. By analyzing these signals, she proposed that inside the outer core there must be another boundary, one that seismic waves were bouncing off. Her conclusion was revolutionary. At the center of the Earth, she suggested, there must exist a solid inner core surrounded by the liquid outer core. Later seismic observations confirmed her hypothesis. The inner core begins at a depth of about 5,150 kilometers and extends all the way to the center of the planet at 6,371 kilometers. Despite temperatures that rival the surface of the Sun, the immense pressure at that depth forces iron atoms into a tightly packed crystal structure, keeping the material solid. Together, these layers form the fundamental architecture of the Earth: crust, mantle, liquid outer core, solid inner core. But the deeper scientists studied seismic data, the more complex this picture became. Within the mantle, enormous structures, sometimes called superplumes, rise from near the core mantle boundary, transporting heat upward toward the surface. At the very base of the mantle, strange regions known as large low-velocity provinces appear to contain unusually hot or chemically distinct material. And within the inner core itself, new research suggests that even this seemingly simple solid sphere may hide additional internal layers. Each discovery reveals that the planet beneath our feet is not a static object but a dynamic system, one shaped by heat, pressure, and movement across unimaginable distances. Yet one question remains at the center of it all: what exactly is happening inside the vast ocean of liquid metal that surrounds the solid heart of the Earth? Nearly 3,000 kilometers beneath the surface, the structure of the Earth changes abruptly. Above this depth, the mantle, though extremely hot, remains solid. Rock slowly deforms over millions of years, flowing under immense pressure. But when seismic waves cross the boundary at 2,900 kilometers, their behavior changes dramatically. S waves vanish completely. P waves slow down and bend sharply. For early seismologists, these observations revealed something extraordinary. The region below this boundary could not be solid rock. Instead, it had to be liquid. This discovery marked the identification of the outer core, one of the most unusual environments anywhere in the solar system. The outer core forms a massive shell surrounding the inner core, extending from roughly 2,900 kilometers to about 5,150 kilometers below the surface. It is composed primarily of molten iron, mixed with smaller amounts of nickel and lighter elements such as sulfur, silicon, oxygen, and possibly carbon. In total, this liquid layer is over 2,200 kilometers thick. To visualize its scale, imagine an ocean of metal deeper than the distance from New York to Denver, completely hidden beneath the mantle. Conditions inside this region are extreme. Temperatures range from roughly 4,000 degrees Celsius near the top to over 5,000 degrees Celsius closer to the inner core. The pressure is immense, reaching more than 1.3 million times the pressure at Earth's surface. Yet, despite these extreme conditions, the iron in the outer core remains liquid. This occurs because the temperature at those depths exceeds the melting point of iron under those specific pressures. Only when pressure becomes even greater closer to the center of the Earth does iron solidify again, forming the inner core. But the outer core is not a calm or static environment. Instead, it is in constant motion. Heat escaping from the deeper inner core creates temperature differences throughout the molten metal. Hotter material becomes less dense and begins to rise, while cooler material sinks. These movements generate powerful convection currents within the liquid iron. At the same time, the entire planet is rotating. Earth completes one full rotation roughly every 24 hours, and this rotation influences how fluids move deep inside the planet. The combination of convection and planetary rotation causes the molten iron to flow in complex, spiraling patterns. These moving conductive fluids generate electrical currents, and those electrical currents create something essential for life on Earth: a magnetic field. This process is known as the dynamo in physics. When electrically conductive fluids move within a rotating system, they can amplify magnetic fields through electromagnetic induction. The flowing liquid iron of the outer core acts as a gigantic natural generator, continuously producing the magnetic field that surrounds our planet. The result is Earth's magnetosphere, a vast invisible shield extending tens of thousands of kilometers into space. Without it, the planet would face constant bombardment from charged particles emitted by the sun. These particles, known as the solar wind, carry enormous energy capable of stripping away atmospheres over time. Scientists believe that Mars once had a magnetic field generated by its own molten core. But when the Martian core cooled and its internal dynamo shut down, the protective magnetic field faded. Over hundreds of millions of years, the solar wind gradually eroded much of the Martian atmosphere. Earth avoided that fate because its outer core remains active. The geodynamo has operated for billions of years, preserving the atmosphere and protecting the surface from intense radiation. Evidence of this magnetic activity is recorded in ancient rocks. When volcanic lava cools, iron-bearing minerals align themselves with the direction of the magnetic field at that moment. As the rock solidifies, that orientation becomes permanently locked in place. By studying these magnetic signatures in rocks of different ages, geologists have reconstructed the history of Earth's magnetic field across hundreds of millions of years. One remarkable discovery from these records is that the magnetic field occasionally reverses polarity. During a magnetic reversal, the north and south magnetic poles switch places. These events occur irregularly, sometimes separated by tens of thousands of years, sometimes by millions. The last full reversal occurred about 780,000 years ago, although the process unfolds over thousands of years. Its existence demonstrates that the geodynamo inside the outer core is a dynamic and evolving system, constantly reshaping the magnetic field that surrounds the planet. Yet the outer core does not operate in isolation. Heat escaping from the core slowly moves upward into the mantle, driving convection currents that influence plate tectonics. In this way, the deep interior of the Earth indirectly shapes the surface world, powering volcanoes, creating mountain ranges, and recycling ocean floors over geological time. But beneath the swirling ocean of molten iron lies an even more mysterious structure. At depths greater than 5,000 kilometers, the pressure becomes so immense that the liquid metal begins to crystallize. Iron atoms compress together into an ultra-dense solid structure. At the center of the Earth lies a sphere roughly the size of the Moon, solid, metallic, and hotter than the surface of the Sun. This is the inner core, the deepest and most extreme environment anywhere on the planet. And for decades, scientists believed they understood it. But new seismic evidence suggests the story may be far more complex than anyone imagined. In the early decades of the 20th century, the internal structure of the Earth was beginning to take shape through the emerging science of seismology. Researchers had already established that beneath the mantle lay a vast liquid outer core, but subtle irregularities in seismic data hinted that the story might not be complete. The breakthrough came in 1936, when Danish seismologist Inge Lehmann carefully analyzed seismic waves produced by large earthquakes. At the time, scientists believed that once seismic waves entered the liquid outer core, they would behave in predictable ways. Yet Lehmann noticed faint signals appearing in places where they should not exist. These waves had somehow passed through a region that behaved like solid material deep inside the core. Lehmann proposed a bold explanation. Within the liquid outer core, there must exist a solid sphere at the center of the Earth. Her conclusion challenged prevailing assumptions about the planet's interior. Temperatures near the center of the Earth were already believed to exceed 5,000 degrees Celsius, hot enough to melt iron under normal conditions. But Lehmann argued that the immense pressure at the center of the planet could force iron atoms into a solid crystalline structure despite the extreme heat. Over the following decades, improvements in seismic monitoring confirmed her insight. Today, scientists recognize the inner core as a distinct layer beginning at approximately 5,150 kilometers below the surface and extending to the center of the Earth at 6,371 kilometers. The inner core has a radius of about 1,220 kilometers, making it slightly smaller than the Moon. It is composed primarily of iron with smaller amounts of nickel and traces of lighter elements. Under pressures exceeding 3.6 million atmospheres, the atoms in this metal are compressed into an incredibly dense arrangement. Despite temperatures estimated between 5,000 and 6,000 degrees Celsius, the iron remains solid because pressure at that depth dramatically raises the melting point of the material. In essence, the force pressing down from the layers above prevents the atoms from moving freely enough to become liquid. The inner core is therefore not only one of the hottest environments on Earth, it is also one of the most compressed. The density of the inner core is estimated to reach around 13 grams per cubic centimeter. more than twice the density of most surface rocks. Yet even though the inner core is solid, it is not static. Seismic studies suggest that the inner core slowly grows over time. As the Earth gradually cools, iron from the liquid outer core begins to crystallize onto the surface of the inner core. Each year, the solid sphere expands outward by a tiny amount, possibly about 1 millimeter annually. This slow crystallization releases heat into the surrounding liquid outer core, helping to sustain the convection currents that power the dynamo. In this way, the growth of the inner core is directly linked to the long-term stability of Earth's magnetic field. But seismic evidence has revealed another intriguing possibility. Some measurements suggest that the inner core may not rotate at exactly the same speed as the rest of the planet. The Earth's surface completes one full rotation every 24 hours. But studies of seismic wave patterns over several decades have hinted that the inner core might rotate slightly faster or slower relative to the mantle and crust. This phenomenon is sometimes referred to as differential rotation. If confirmed, it would mean that the inner core is not rigidly locked to the rest of the planet but instead moves independently within the surrounding liquid metal of the outer core. The motion is extremely subtle, perhaps only a fraction of a degree per year, but it reveals how dynamic the deep interior of the Earth may be. Understanding this movement is difficult because the inner core cannot be observed directly. Scientists must rely entirely on the behavior of seismic waves passing through it. By comparing wave travel times from earthquakes occurring decades apart, researchers can detect tiny changes in how those waves move through the planet's center. These measurements require extraordinary precision. A difference of just a few tenths of a second in seismic wave travel time can reveal changes occurring thousands of kilometers below the surface. In recent years, some researchers have proposed that the inner core might even oscillate, gradually speeding up and slowing down relative to the rest of the planet over long timescales. The cause of this motion could be linked to gravitational interactions between the mantle and the magnetic forces generated in the outer core. Yet the deeper scientists analyze seismic data, the more unexpected patterns emerge. Some waves appear to travel faster through certain parts of the inner core than others, suggesting that its internal structure may not be uniform. Instead, iron crystals inside the core might be aligned in specific directions, creating regions where seismic waves move more isolated along one axis than another. This phenomenon, known as seismic anisotropy, hints that the inner core may have developed complex structures during billions of years of slow growth. And in the past decade, researchers studying high-resolution seismic data have uncovered an even more surprising possibility. Within the inner core itself, there may exist another hidden boundary, a smaller region at the very center of the planet with a distinct internal structure. If confirmed, it would mean that the Earth's center is not a single uniform sphere, but a layered structure even more complex than previously imagined. A hidden core within the core, and its existence could hold clues to how the deepest part of our planet formed billions of years ago. For decades, the discovery of the inner core seemed to complete the picture of Earth's deepest structure. Beneath the mantle lay a liquid outer core, and inside it, a solid metallic sphere roughly 2,440 kilometers across. The model was elegant and, for many years, consistent with the available seismic evidence. But as seismic technology improved and global monitoring networks expanded, scientists began detecting subtle signals that did not quite fit the established model. Seismic waves traveling through the center of the Earth sometimes behaved differently depending on the direction they took. Waves passing along paths parallel to the Earth's rotational axis appeared to travel slightly faster than waves moving through the equatorial direction. This phenomenon suggested that the inner core was anisotropic. Its internal structure allowed seismic waves to move more easily in some directions than others. At first, researchers believed this effect was caused by the alignment of iron crystals inside the inner core. Under immense pressure, iron atoms arranged themselves into tightly packed crystal lattice. Over time, the growth of the inner core may have caused these crystals to align preferentially along certain orientations, affecting how seismic waves propagate. But new observations began to suggest something even more unusual. In the early 2000s, geophysicists analyzing decades of earthquake data noticed that some seismic waves traveling through the deepest center of the Earth behaved differently than those passing through the outer portions of the inner core. The differences were small but consistent. Waves that penetrated the very center of the planet appeared to slow slightly and change their propagation patterns. This leads scientists to propose the existence of an innermost inner core. According to this hypothesis, the inner core itself may contain a smaller central region with a distinct crystalline structure. Instead of being a single homogeneous sphere, the core could consist of two nested layers, each formed under slightly different conditions during Earth's long geological history. Seismic studies suggest that this innermost region may have a radius of roughly 600 to 650 kilometers. If confirmed, it would represent a previously unknown boundary at the very center of the Earth, one that cannot be observed directly, but can be inferred through careful analysis of how earthquake waves pass through the planet. Why would such a structure exist? One possibility involves the way the inner core has grown over time. As the Earth gradually cools, iron from the liquid outer core crystallizes onto the surface of the inner core. This slow accumulation adds new layers of solid metal over hundreds of millions of years, but conditions inside the Earth have not remained constant. The rate at which heat escapes from the core into the mantle may have changed over geological time. Variations in mantle convection, shifts in tectonic activity, or changes in the chemical composition of the outer core could all influence how the inner core forms. If the environment surrounding the inner core evolved over billions of years, the earliest portion of the core, the material at its very center, may have crystallized under conditions different from those that formed the outer portions of the inner core. This would produce layers with slightly different crystal orientations and structural properties. In other words, the deepest center of the Earth may preserve a geological record of the planet's earliest internal history. Seismic evidence also continues to fuel debate about how the inner core moves relative to the rest of the planet. For years, some studies suggested that the inner core might rotate slightly faster than the Earth's surface, completing an additional rotation every few hundred years. This phenomenon, sometimes called superrotation, was proposed to explain long-term changes observed in seismic wave travel times. However, more recent research indicates that the motion of the inner core may be more complex. Some datasets suggest that the inner core could oscillate, alternately rotating slightly faster and slightly slower than the mantle over multi-decade timescale. These changes may be driven by gravitational forces exerted by the surrounding mantle, as well as magnetic interactions with the flowing liquid iron of the outer core. The movement involved is extremely subtle, measured in fractions of a degree per year, but it highlights how dynamic the deep interior of the Earth may be. The existence of these internal variations has major implications for understanding how the core influences the entire planet. Changes in the inner core affect heat flow into the outer core. Heat flow influences convection currents in the liquid metal. Those currents control the strength and behavior of the geodynamo, which produces Earth's magnetic field. In other words, processes occurring thousands of kilometers beneath the surface may ultimately shape the protective magnetic shield surrounding the planet. Yet despite decades of research, the center of the Earth remains one of the least understood regions of our world. Every new earthquake recorded by global seismic networks provides another small piece of evidence, another vibration passing through the planet's deepest structures. And with each new data set, scientists refine their understanding of the hidden heart of the Earth. But the core is not merely an isolated metallic sphere. It is the engine that drives the long-term behavior of the entire planet, more than 6,000 kilometers beneath the surface. Far beyond the reach of any drill or instrument, the Earth's core operates as a vast engine that quietly shapes the behavior of the entire planet. Its influence is not immediately visible. No volcano connects directly to the core. No mountain reveals the forces at work thousands of kilometers below. Yet the energy generated in this hidden region ultimately drives processes that define the surface world. The story begins with heat. Earth formed in a violent environment billions of years ago. The impacts that built the planet released enormous amounts of energy, leaving the interior extremely hot. In addition, radioactive elements inside the mantle and crust continue to generate heat through radioactive decay. Some of that heat originates in the core itself. As the inner core slowly crystallizes, iron solidifies from the surrounding liquid outer core. This process releases latent heat, which rises through the outer core and into the base of the mantle. At the same time, chemical separation during crystallization releases lighter elements into the outer core, creating additional buoyancy that fuels convection. These heat and compositional differences keep the outer core in constant motion. The movement of molten iron sustains the geodynamo, generating Earth's magnetic field. Without this process, the magnetosphere would collapse, exposing the planet to intense solar radiation and gradually eroding the atmosphere. But the core does more than power the magnetic field. Heat escaping from the core also influences the behavior of the mantle, the enormous layer of rock that extends from the base of the crust to the core mantle boundary. Although the mantle is solid, over geological time it behaves like a very slow-moving fluid. Hotter, less dense rock rises upward while cooler material sinks downward. These mantle convection currents transfer heat from the deep interior toward the surface. This slow circulation drives one of the most important geological processes on Earth, plate tectonics. The surface of the planet is divided into massive slabs of crust known as tectonic plates. These plates float atop the slowly moving mantle, drifting across the surface over millions of years. Where plates move apart, new ocean crust forms at mid-ocean ridges. Where plates collide, one plate may sink beneath another in a process known as subduction, generating powerful earthquakes and volcanic arcs. These tectonic processes reshape the planet's surface continuously. Continents shift position, mountain ranges rise and erode, ocean basins open and close. The energy that sustains this long-term geological activity ultimately traces back to the heat flowing out of the Earth's deep interior, including the core. At the boundary between the core and the mantle, temperatures may exceed 4,000 degrees Celsius. In some regions, this heat produces enormous upwellings of hot mantle material known as mantle plumes. These plumes can rise thousands of kilometers toward the surface, eventually producing volcanic hotspots such as those responsible for the Hawaiian Islands. Other structures near the core mantle boundary remain less well understood. Seismic imaging has revealed enormous regions beneath Africa and the Pacific Ocean where seismic waves travel unusually slowly. These structures, known as large low-shear velocity provinces, may represent zones of extremely hot or chemically distinct material. Some scientists believe these deep regions could influence the formation of mantle plumes and long-term tectonic activity. Despite decades of research, the interaction between the core and the mantle remains one of the central mysteries of Earth science. Even the future of the core itself is a subject of ongoing investigation. Over billions of years, the Earth continues to cool gradually. As heat escapes into space, the inner core slowly grows as more iron crystallizes from the outer core. Eventually, far in the future, the outer core may cool enough that convection slows dramatically. If that were to happen, the geodynamo could weaken or stop entirely, causing the magnetic field to fade. However, current estimates suggest that such changes would occur only after billions of years, long after the sun itself begins to evolve into a red giant. For now, the deep interior of the Earth remains active, hidden beneath layers of rock and metal. The core continues to generate the magnetic field, release heat, and influence the dynamic systems that shape the planet's surface. Yet despite everything scientists have learned, the center of the Earth remains one of the least accessible environments in existence. No human will ever stand there, no probe will likely ever reach it. The only clues come from faint vibrations, seismic waves traveling through the planet after earthquakes. Each tremor provides another glimpse into the structure of the world beneath our feet. Through these signals, scientists have reconstructed a picture of Earth's deepest regions, a molten ocean of iron surrounding a solid metallic heart, possibly layered and evolving slowly over billions of years. At a depth of 6,371 kilometers, the center of our planet remains unseen, unreachable, and yet profoundly influential, an invisible engine sustaining the world above it.